In this video, we're going to quickly review some concepts from probability theory, just so that we have an ample source of examples later. A probability density function on a set omega is a function p from omega into the real numbers such that one p of x is greater than or equal to 0 for all x in omega. 2, if omega is finite, the sum over x in omega p of x is equal to 1. If omega is continuous, p is integrable in some suitable sense, and integral p of x dx is equal to 1. So this basically says, and what the probability density function basically encodes is the relative frequencies of a particular outcome x. In particular, those frequencies always have to be positive, and they always have to sum to 1. That is, something always has to happen, right? Probabilities go on a range from 0 to 1, or relative frequencies of outcomes go on a range from 0 to 1, and they don't go lower, they don't become negative, and they don't go higher. Now, once we have a probability density function, we can define a random variable. A random variable on a set omega is x, which is distributed according to a PDF probability density function P, and we say that P is the law of x. So all we're saying is that, well, we have this probability density function and we have some random number that we're going to get, and it obeys this relative frequency law, which is determined by P. That's it. For example, we can have omega is equal to 0, 1. And we can say that x, a random variable on omega, has law p satisfying p, the probability that x is equal to 0 is equal to 1/2, and the probability x is equal to 1 is 1/2. And such a thing where I have a 0, 1 outcome is called a Bernoulli random variable. The only thing that changes about a Bernoulli random variable is the different values of the two events, right? So this can be any number a from 0 to 1, and this has to be 1 minus a. That's the only thing. And it's a very useful distribution. It shows up all the time. So let's suppose that I have a random, I have a coin, and I flip it heads or tails, which I'll denote 0 and 1. So tails is equal to 0, say, and heads is equal to 1. I'm going to flip it, that is, I'm going to run a bunch of Bernoulli trials, and I want to know if it's a fair coin or not. And so I build up this table. Let's say I flip it 50 times. And let's say I get the outcome, so I flip it 50 times and I get a 28 here, and say not a 32, and a 22 here. So I get 28 tails and 22 heads. Well, I can take the average, right? So now I've got that these are actually 0 and 1, right? Well, the average, according to this rule, right? So the average value of this random variable or random sample, well, I sum over all the samples xi, I equals 1 to 50, and then I divide by the number of samples. Well, if I sum I equals 1 to 50, I'm going to have exactly 28 zeros, so this will be 1 by 50 times 28 times 0, plus I'll have 22 ones. Ultimately, this means that my sample mean is 28, 50 times 0 plus 22, 50 times 1, which will just be 22 over 50. But if you look at this guy, this is a relative frequency of an event. This means that we can write our average of a random sample, our sample mean, in terms of relative frequencies times the value that are obtained with those relative frequencies, and then we sum them up. And this motivates the definition of expectation with respect to a random variable. So definition, let f from omega into r be a integrable function. And suppose x is a random variable with law p, then the expectation of the random variable, well, x is a random variable on omega, of course, so the random variable f of x is, we'll denote e f of x, and it's simply the integral, or the sum, of f of x, p of x, dx. So for example, let omega be the set from 1, the first 6 integers. And let's suppose that probability x is equal to a particular x, where x goes from 1 to 6, is equal to 1/6. So that is, I have a fair 6-sided die. Then what's the expected value of the random variable x obeying this law? Well, it's going to be 1/6 times 1, right? So it's just the sum of the probabilities times the value of x, plus 1/6 times 2, plus 1/6 times 3, plus 1/6 times 4, plus 1/6 times 5, plus 1/6 times 6. Ultimately, that will give you 3.5. So the expected value when I roll a die is 3.5, even though that number doesn't actually occur in any of the events. It just is what one would expect on average if you took sample means, right? If you rolled this die a bunch of times, then you would expect to find this number, and that's simply the law of large numbers.